Hello and welcome to this new episode of Not So Fast. In this video we are going to discuss probability and in particular how it's conceptually quite difficult to define it. So we are going to start by looking at a simple example, and this simple example is that of a six-sided die. Now if we throw the die once, then the set of all the possible outcomes is going to be the number of spots that can be looked at once the die has settled down on top of it. Now, what people do is that once they have done this, then they can assign probabilities to each of these outcomes. Now, what the classical probability theory demands is that these P1, P2, P3, P4, P5, P6 are real numbers, which are each between 0 and 1, and that the sum of these probabilities add up to 1. Now, one thing that we can look at is what happens if we want to calculate the probability to obtain an even outcome. In this particular case, we are going to have that the probability of an even outcome is going to be the probability of finding 2, which is an even number, plus the probability of finding 4, which is also an even number, plus the probability of finding 6. So we add up the probabilities. If I rephrase it in terms of what we've seen before, this is going to look like P2 plus P4 plus P6. Basically, that's it. From probability theory alone, the only thing we can get is this particular general equation, that the probability of getting an even number for the outcome is a sum of these three probabilities for a six-sided die. So how can we move a bit further from this? Well, there is a very popular model which is called the fair die model. This fair die model mathematically requires that the probability 1 is equal to the probability 2, etc., so that they are all equal to each other and then denoted by the same letter P. Now, it also demands, and that's something we've written before, that the addition of all these probabilities equals to 1. But because we know that they are all equal to each other, we end up with the following equation to solve. 6 times P is equal to 1. As a result, we can get that the probability of each outcome is 1 over 6. Now, if we come back to our even problem, we've got that the probability of finding an even outcome after one throw of the die is the sum of P2, P3, and P6. Now, if I replace by the values we've talked about earlier, this is 1, 6 plus 1, 6 plus 1, 6. So we are going to find that this is 3, 6. Now, of course, we could here simplify further into an equivalent fraction, which would be 1 over 2, but that's not what I want to do at that stage. Instead, I want to reinterpret this in terms of a very common formula, which is the following one. So that's the probability of an event would be equal to the number of favorable outcomes divided by the number of possible outcomes. So here, for P of even, there are 3 favorable outcomes that are even, and there are 6 possible outcomes in total. So 3 over 6 does satisfy this particular formula. This is in fact obviously very well used. If you look at introductory level of probability theory, likewise on this one and on this one, for example. The issue that may come with this is that it can be confused by a definition of probability. The issue then is that because we've seen that this only works in the fair die model, where, for example, all outcomes have the same probability, then it follows that this particular equation is only true with equiprobable outcomes. So it cannot serve as being a general definition for a probability or even a practical formula to find probability values. So this actually underlines a much bigger problem with probability theory in mathematics. And this particular problem, or at least feature, is the following. And I'm going to explain it in this bubble. Essentially, what happens is that probability theory enables to find new probabilities from pre-existing probabilities. It's not able to create probabilities, ab nihilo, so from scratch, from some kind of vacuum or anything like this. So in sum, the mathematical theory of probability does not permit free lunch. Okay, so you can't create probabilities from nothing. So we have seen here that the mathematical theory of probability only enables to transform some probabilities into other probabilities. Now the issue with this is that we can obviously wonder, where do these probabilities come from in the first place? And how do we conceptually define them in this particular instance? Now it turns out that one way, which is very popular to do so, is a so-called Frequentist approach. Let's say in the case of our die, we throw the die n times. Okay, and n can be 10, but it can be also 1 million, 1 billion, whatever you want. Okay, so we throw a die n times, and then these are the possible outcomes of each of the throwing experiment. And what we are going to display here are basically the histogram of frequencies of occurrence of every single outcome. So here it's entirely made up, but let's say you could find something like this. Now, what we are going to call, in some sense, the probability, or at least we can relate it to, is the following thing. So, for example, the probability P2 would be roughly something like the number of times you get, let's say, 2 spots for when you throw the die over the total number of trials. Now, there are two issues with this particular strategy. The first one is conceptual and pertains to something called the law of large numbers. Now, what it says is the following. If you take the frequency of obtaining the number 2 over n trials, and you subtract to it the actual unknown probability of obtaining 2 spots. If you take this difference and you basically take the positive value of that difference, right? So it could be negative initially, but it doesn't matter. You take simply the positive value, and then you check what is the probability for this difference to be larger than some error. Then what mathematics says is that the probability for this difference to be larger than some error is approximately, less than or equal to 1 over n, the number of trials, times this error squared. Now the important bit here is that you see that if the error is fixed, then the number n here, as it is being increased, is going to decrease the probability for the difference to be larger than that error. And eventually, if the error is fixed, then you are going to get a probability which tends to 0 as n tends to infinity. All right, so this is basically illustrating the intuitive idea that we have that the probability is going to be very much close to the frequency of occurrence of these, for example, number 2 spots. Now, the problem with this is that we need a probability here to define a probability, right? So the probability for getting this difference larger than some error is a probability. So essentially we are running a little bit in circles, because conceptually, to define the probability of obtaining 2 spots, we need actually the probability for the difference between the frequency and P2 to be larger than some error. And so we could actually either stop here and say that we need a probability to do so, or if we want to define then this new probability of the difference being larger than some error, then we would need again to plot some kind of histogram, having a frequentist interpretation, and then we would have yet another probability of the difference and so on. So it's a never-ending story. So either we basically run into a circular argument, or we run into a so-called infinite regression when it comes to this definition. So there is a big conceptual issue here. Now there is also another issue, which is in that case practical. And the problem is the following. Is it possible to carry out the same random experiment over and over again without altering its characteristics? And here this is really something that asks ourselves whether the mathematical or conceptual definitions we come up with for probability can be carried over when we use that in the real world. And in particular, here let's take you have a die, and the first outcome, for example, let's say would be on number 2. Now what I'm going to show here is what could happen as you roll the die over and over and over again, let's say like few thousands or millions of times. Then eventually you will see something like this. The shape is going to change because of wear, and eventually this is going to be very, very far from the initial shape you started with. And this is something, of course, that then compels us to think in what sense then do we define or can we talk about the probability of some event occurring, and to what extent can it be used in reality. Right, so in this short video what we have seen is that probability is a very elusive concept. Mathematically it's well defined, but what it comes to is that the mathematical formalism enables us to get probabilities from pre-existing probabilities. If we try to go a bit deeper and try to find how these pre-existing probabilities can be found and actually defined, conceptually defined with, let's say, more tangible concepts, then we run into trouble. And the point here is that the frequentist approach and the practical problem we've presented are obviously very important problems in the theory of probability, like the philosophical and foundational aspects of probability theory. There are other theories or, let's say, concepts or interpretation of probabilities, but for the most part, all of them have their own caveats. And that's why there is basically an ongoing fight between the different sides or camps when it comes to how to interpret and measure and apply probabilities. Now, if you're interested in any of these alternative interpretations, which I've not yet discussed in this video, then just let me know in the comment section, and I would be happy to make a second video on this and discuss these other interpretations and their caveats. Now on this, I leave you and see you in the next video.